the first week is a lot of introduction material, and we actually say really useful things during this first week. It may not feel that way. A lot of things that we say today and tomorrow and Friday and Monday, they're going to feel like, oh, these things are so obvious. It's like, oh, these things are things I already know. Is there really much to learn here? Yeah, there's some good stuff here. There's some good stuff here. All right. So we're going to start by just talking about one of the sort of things that you might be able to do. So first off, I hope that you become convinced very quickly that solving differential equations is not easy. It can be challenging. If you don't believe me, just think back to Calc 2 and think about how hard it was to integrate. And this is like integration plus plus. So there's even more going on. The good news is it is easy to verify a differential equation. And why do we say that? Well, to verify, what we do is we just check if it works. It's so simple. And so how do we do it? Well, we take our solution and plug it in and see if the relationship is satisfied. So here's an example. So verify that this function, y, which is x times e to the 3x plus 3x squared plus 4x plus 2, is a solution of y double prime minus 6y prime plus 9y equals 27x squared. Now you'll notice it emphasizes the word a. There's many solutions out there, but this is one of them. We just want to verify it. So what do? Well, we say, all right, here's our function. Y equals x e to the 3x plus 3x squared plus 4x plus 2. Now we need to plug it into this equation. That means we need y prime and we need y double prime. All right, y prime. What is it?
Oh, is it 3x to the e to the 3x power?
Okay, 3x e to the 3x power. All right.
Let me keep going. Okay, plus 6x.
Plus a 6x.
Plus 4.
Plus 4.
And then that suspicious gap.
There is a suspicious gap there. There is a very suspicious gap, as if something should go in that gap. E to the 3x should go there. Why is there an e to the 3x showing up there? Product rule, right? Because it's x times e to the 3x. And so we need to use the product rule. This is all right. This is us getting back into these things. We're going to get good at it. We'll get better. No problem. Y double prime. All right. Are you willing to trust me if I write something down? Are you going to challenge me? All right. At least one person says, yes, I trust you. A lot of people are like, I don't know, I'm pretty skeptical, Steve. But, all right. So I claim 9x e to the 3x plus 6 e to the 3x plus 6. Now, there's a lot of people who will say, yeah, I see that 9x e to the 3x, no problem. But that 6 e to the 3x, that's kind of weird, Steve, because if I take the derivative of e to the 3x, I should get 3 e to the 3x. Where did that 6 come from? Well, there'll be another 3 e to the 3x from here. So there's a 3 e to the 3x by taking the derivative of the x term, keeping the other term alone. And there's a 3 e to the 3x coming from there. Okay, so now we have our y prime, our y double prime. And so, what do? Well, say, look, I need 9 of the y's, because that's what we have there. Then I'm going to subtract off 6 of those y primes. And I just need 1 of these y double primes. And let's see what we get. So on the left-hand side, y double prime minus 6y prime plus 9y equals. All right, let's do this. Okay, 9x e to the 3x minus 18x e to the 3x plus 9x e to the 3x gives us 0. That's good. We don't want any x's, e to the 3x's, because there aren't any over there. That's a good sign. There's no e to the 3x there, but minus 6 e to the 3x plus 6 e to the 3x gives us 0. Good. Oh, great. 9 times 3x squared gives us 27x squared, and there's no other x squareds. So, all right, so there is a 27x squared. All right, 9 times 4, 36. 36x. Minus 6 times 6, minus 36x, and then there's no x. 36 minus 36, 0. As if it was meant to be, because it was. 9 times 2, 18. 6 times 4, 24. And we're subtracting that. 1 times 6, 6. Put them all together, we get 0. And therefore, we get that, which means we are happy because it worked. We see that for this choice of y, when we take our derivatives and replace the derivatives with the proper form, everything balances out exactly as it should. Now you might say, well, this is great. I mean, if I have a problem like this on the homework, it's like, okay, just check it, verify. Is it good for anything else? Well, this is a useful tool, because one of the things that happens is oftentimes when we're solving differential equations, there can be many steps. And when there are many steps, that means many opportunities for us to make a mistake. But we don't want that. We don't want to make a mistake. But we'd like to know at the end if you got it right. So there's kind of two options. One option is redo all the work. That's hard. Plus, it's likely that you're going to remake the same mistake. What's the other option? Check your answer, right? So instead of redoing the work, we say, look, there's this built-in way. We just plug it in and say, hey, I have what I think is an answer. I'll just quickly check to see if it works. So this is one of the things you can do with this tool. It says, hey, I have an easy way to find out if I got the right answer. I also have an easy way to find out if I made a mistake, to check myself. So, as the great mathematicians say, you should check yourself before you wreck yourself. So, there you go. So this is one of the things you can do with this sort of idea of verifying a solution. All right, on to our next one. Find all of them. Wow, maybe there's a bunch of them. All the values of r. So that y equals e to the power rx is a solution of something. All right, so there's a differential equation here because there's derivatives involved, so that's how we know it's a differential equation. But there's boxes. That means we get to fill in the box with some numbers. All right, so what goes into the first box? What number do you want there? 2. The second box?
1.
The third box?
0.
Let's not do 0. Let's 3. 3. All right. 2, 1, 3. Great. A choice has been made. So we have this differential equation, 2y double prime plus y prime minus 3y equals 0. Now you'll notice something. Most of the time when we ask for people to give us random numbers, that's a dangerous thing to do when integration is involved. This is a really special case, and we're going to love these kinds of problems. So this is a foreshadow of things to come. That these kinds of problems can be done in really cool and beautiful ways. And the reason it works out so nicely is because this is a nice function, e to the x. And there's a general thing to keep in mind, namely that we love e to the x. That should be sort of our mantra in differential equations. We love that function. Now, what's so great about e to the x in terms of differential equations? What's so nice about this function? It's its own derivative, right? Yeah, that's such a cool thing. And there's even more cool stuff, which we'll talk about as we go forward with this problem. But why is it so cool that it's its own derivative? Well, that says, look, when I'm taking derivatives, it's basically the same thing I started with. It doesn't change much. And so when things don't change much, it feels like it's easier to control things. When things start changing a lot, things start feeling out of control. And we like to be in control of our lives. So we love the exponential function. All right, well, so what do we have? Well, we have y equals e to the rx, and r is a number. What is y prime? R e to the rx. What is y double prime? R squared e to the rx. Yeah, fantastic. Okay, so now we're going to put these in the right places. I probably should have gone in the other direction. There we go, yeah. So 2 r squared e to the rx plus r e to the rx minus 3 e to the rx equals 0. All right, so now if we have a solution, if there is a value for r, this must be true. What do we do? What do we do? Factor out e to the rx? Okay, all right. Why? Well, it's common. All right. Factor out e to the rx. 2r squared plus r minus 3 equals 0. Okay, so we factored out, it's a common term. Now, what comes next?
You can do a quadratic formula from the polynomial.
Okay, so there is a polynomial here. This 2r squared plus r minus 3 is polynomial, and so we can work with it. Of course, we might want to try to factor it first. Yeah, I don't think we want to try to factor that one. Why did you leave this other piece, this e to the rx? Why did you say, like, I don't care about e to the rx? Why can we ignore it?
Because you can just divide both sides by it.
But why can we divide both sides by it?
It's not 0.
Oh, in the back?
Because e to the rx can never equal 0.
Yeah, e to the rx can never equal 0. Remember how we said we love e to the x? This is another reason we love e to the x. E to anything is never 0. And so what we have is this part, that's not 0. And we multiplied it by this other thing, and we got 0. So this other thing, it has to equal 0. So we have this polynomial in r that r has to satisfy. Okay, well, all right. Quadratic formula. Do you remember the quadratic formula? Negative b plus or minus square root of b squared minus 4ac all over 2a. Good. You're very concerned about that last part. You know, it's like 2a. Yes, in the back. Does it factor? Wow. Do you guys choose easy numbers?
I was going to divide the last one.
2r plus 3 times r minus 1. This would have worked too, of course. You know, we were going to make our 7th grade math teachers proud. They were like, I remember it. You were a good teacher. My favorite teacher until this semester. Okay. All right. So 2r plus 3 times r minus. Okay, I think, you can always check, right? 2r squared minus 2r plus 3r. That's r minus 3. Yeah. Wow. That's an amazing coincidence. Okay, so what do we end up with for our choices for r? So negative 3 halves and 1. Now, because it asked for values of r, and this is one of the tricks. When you're doing a problem, you should make sure you know what you're looking for. So we're looking for the values for r, which means we're done. Now, we can also say, all right, what does that tell us about the solutions? Well, it says 2 solutions, because we have 2 values for r. One of them is e to the minus 3 halves times x. And another solution is just e to the x. So those are our solutions to that particular differential equation. And there we go. Wow, cool. We're like doing it. We're like real differential equationers. Or I'm not sure how you phrase that, but we can do differential equations. Good, good. All right. Well, let's keep going. So the next thing is the idea of initial value problems. Now, this is a case where the name is very descriptive. Namely, we have a problem with an initial value. So what is that? Well, what it tells us is we have a differential equation. And when we have a differential equation, generally speaking, there's lots of potential functions out there. Remember that plus c that you often saw when you did antiderivatives? It says, oh, there's many possible antiderivatives. So when you have a differential equation, there's many possible functions. But when you add in some extra constraints and say, well, I want the function that does this. Another way to think about it is, I want the function that starts here. So the initial values are saying what's happening initially. And then the differential equation says, okay, here's how you're going to change. So we can combine that information. Where am I at initially? How am I changing? And then all of a sudden, I can figure out everything I want to know. I can just follow the change to get to where I'm at. So this says, lo and behold, we want to find the function is the goal. If it's possible, sometimes it's not always possible. We'll might have time to see some examples. Now, the number of constraints, this is the number of conditions that we have to be given, is the order of the highest derivative involved. So if I have a first derivative as the highest derivative, one constraint. I need to know something about where the function is. If I have two derivatives, I need to have two pieces of information. And we'll do an example that involves a second derivative in a moment. But let's start with an example that involves just a single derivative. So here we go. Verify that this function, log of x plus c, is a solution of e to the y prime equals 1. Okay, there's one sentence. Second sentence, find the particular, and look at particular, so I can emphasize particular solution of the function, which also satisfies y of 0 equals 1. Okay, so this right here, this y of 0 equals 1, this is our initial value. So that's when we talk about an initial value problem, that's what we are referring to, is this piece of information here. All right. Well, we should do the first part. Verify, that's not so bad. We just say, okay, well, we start e to the natural log of x plus c, and think of c as a constant, times the derivative of natural log of x plus c, which we'll denote as log of x plus c prime. So that just says I'm taking the derivative of the inside. Well, okay. E to the natural log of x plus c, what does that become? X plus c, because e and log are inverse functions of each other. The derivative of the natural log of x plus c, what is that? 1 over x plus c. And what happens? Yeah, they're equal. There's cancellation. Bum, bum. Giving us 1. And lo and behold, see, this is our e to the y. Here's our y prime, and it does equal 1. Check. So we've finished the verification. When we plugged it in, it worked. Verify is the fun part. Well, that sort of implies there's a non-fun part. It's all fun. It's all fun. All right. Well, now find the particular solution. So when we're asked to find the particular solution, we're really saying, find the right choice for C. What's the best choice for C that gives us just what we need? Okay, so we need 1 to be y of 0. I know what y should look like. So that's natural log of 0 plus c, because I'm plugging in x equals 0. So is there some number, when I take the natural log of it, I get 1 out? E. So that tells us, aha, c should equal e. Now, we're not after c, we're after the solution. And when we're talking about solution to differential equations, we mean the function. So our answer would be y of x, or just y. Oftentimes we just suppress the of x, is the natural log of x plus e. And there we go. There we go. We're differential equationing now. That's good. That's good. All right. Any questions on that one? Good. Let's kick it up a notch. Okay, so find the function y which satisfies y double prime plus y equals 0, y of 0 equals something, and y prime of 0 equals something. There's boxes. Let's put something in our boxes. What do you want y of 0 to be?
13.
13? Okay. All right. We have space. Y prime is 0? 7. I think we have space. All right. I hope. I hope. Now, have we seen y double prime plus y equals 0? I hope this looks familiar, because it should be familiar. So what?
Like the spring?
Spring? Is it?
Is it the sine function?
It is the spring problem. It's a problem we did last time. Like, what? We have to remember stuff? That's terrible. Yes? Yeah, so remember when we talked about the spring problem, we have either the sine function or the cosine function. And so we said, oh, hey, here's the general form. The most general way we could write it is if we had y as submultiple times sine, and then submultiple times cosine. So this feels like a little bit like, wait, where did it come from? Well, this is what we talked about last time. And in some sense, it was a matter of like, oh, we were able to recognize certain functions that work. All right, great. So let's just take it. Now notice, we have A and B. That says there's two things we get to choose. We get to choose a value for A and we get to choose a value for B. So I should have two pieces of information that help me make the right choice, because I must choose. And choose wisely. For as the correct choice brings us closer to the answer, a wrong choice will take us further from it. But that's okay. We now apply what we have here. So what do we have? Well, plug in 0. So at 0, what do we see? Well, y at 0 is 13. That should equal a times sine of 0 plus b times cosine of 0. Do we know what sine of 0 is? 0. That whole first term, gone. How about cosine 0? Cosine of 0 is 1. All right, so what can we conclude now? Yeah, we come to the conclusion b equals 13. Good. That wasn't so bad. Now the other constraint is at y prime. So we better write down y prime. So what is y prime? Okay, a cosine x minus b sine of x. All right, and then at 0. Well, y prime at 0 is supposed to be 7. So that's a cosine of 0 minus b sine of 0. Well, sine of 0 hasn't really changed much, so that knocks the second term out. And neither has cosine of 0, still the same. So, what do we conclude? A is 7. Aha! We had enough space. So, our function is 7 sine of x plus 13 cosine of x. And life is good. Life is good. Now, I'll do the dangerous thing and ramble for a few minutes here. There's this asterisk I put there, which is the number of constraints is the order of the highest derivative involved. And so when there's just a first derivative, there's really not much to worry about. When there's a second derivative, things can get dicey. in the following sense. You should always ideally have all your constraints at a particular point. So in other words, at the same point, but just like work your way up when derivatives. Y is 0, y prime is 0. You can, in principle, have constraints happen at different points. So maybe I could say, I want to have the spring be here at 0 and be here at time pi thirds. But once you do that, you start opening yourself up for trouble. There's a can of worms, and so you should avoid that if possible. Now, are you willing to indulge me for a second to sort of show you why you can get in trouble? Yeah. So here, we'll just make one small change. Y of 0 equals 13, and y of pi equals 7. So it says I want my spring to be stretched to length 13 at time 0 and to length 7 at time pi. Now that's two pieces of information. In principle, that should be enough. In principle. So we say, okay, great. We still have the same general form up here. So we say, all right, at time 0, what happens? Well, we get a times sine of 0 plus b times cosine of 0 equals 13. Conclusion, b equals 13, because it's exactly the same thing we saw here. What happens at pi? Well, a sine of pi plus b times cosine of pi has to equal 7. What's sine of pi? Still 0. What's cosine of pi? -1. And now we come to the conclusion that b equals -7. Wah, wah, wah. What's the problem? These are bad things. Crying. It's like we just cut some onions. We run into this impossible situation where we have that b has to be two different values simultaneously. And so when you start fiddling with your initial conditions and saying, oh, mix a little bit here and mix a little bit there, you might lead to some impossible situations, which is why you should ideally always have your initial conditions at the same place, which is probably what you'll see the whole semester. But anyways, all right. Yes, there's a question.
If y of pi was instead y prime was pi, then it would have been a problem, right?
Right. Yeah, it's not every time when you mix initial conditions that you run into problems, just sometimes. And there's other weird things that can happen. This is just one example. But yeah, I'm not saying that it's always going to be bad. I'm just saying it could be bad, so take it with a grain of salt. Yeah, you're right. We rigged it. We rigged it. Which is what we do all the time in math problems. We always choose the nice ones, or the really bad ones. We never usually choose the middle ones. Okay, so a little detour. And I should say we are following pretty closely with what the book does here. So if it feels like we're like jumping around a little bit, it's because we're sort of jumping around a little bit. But I want to try to hit what the book hits. You should still read the book. You've in theory paid for it somehow, so you might as well. So there's this notion of mathematical modeling that gets talked about, but don't worry too much about what this is. Just sort of, I want to say it's a philosophy. And when we talk about mathematical modeling, it's not just a mathematical type of philosophy. It's really a more general scientific type of philosophy. How do we develop ideas? Well, there's sort of this process that happens where we say, well, we think about what's going on and we formulate, this is what we think should be true. And oftentimes in that formulation, we'll derive a formula and say, oh, here's this differential equation that's a consequence of how we think about the way the system should work. And now we analyze. And this part right here, going from the formulation to the analysis, this is where the solving of differential equations is coming into play. So we come up with and say, okay, if this is how you think it should work, here's the function that does what you think it should. Then after we have this function, we look at it and say, well, let's think about what this tells us. And does it make sense? Is it reasonable? And if it is, we're happy. But oftentimes we say, I think we should do a little bit better. There's something else going on here that is not being properly captured. And so what do? We go back and say, let's try again. Let's fix it in some way. And then we get a cycle. So this is oftentimes how science works. The way you're presented with science now is it sort of seems very linear. It's like somebody had an idea that seemed very obvious, and then people said, yes, it was obvious, and now it's accepted as truth. And there's a beginning, a middle, and an end. But that's not really the way it goes. There's a whole process where people said, I have a guess. Here's what I think happens. And people said, ha, you missed something. Okay, here's a new guess. And it keeps going and going and going. And there was an article in the New York Times in the last week that said, hey, one of the things that is happening because of the current situation with COVID is people are learning about the scientific process. We learn and then we improve on our understanding. So it's great. Wow. Not the way we should learn science, but okay. At least we're learning. So we'll do some examples. So we'll start with Newton's law of cooling. This is named after Isaac Newton. This is not named after the fig Newtons, where it's like, okay, you make a fig Newton, pull it out of the oven. How long does it take to cool? No. Isaac Newton. So you can imagine that you have a cold environment, like say a refrigerated space. And what we're going to do is we're going to put into that environment something which is very warm. Maybe we've heated up a piece of metal and ingot or something. So we have this burning hot thing that we put into this cold environment. Now the environment is such that it will always stay the same temperature. What happens to this object that's now been added in to this space? Well, if it's a hot object in a cool space, it will start to cool. All right. So Newton said, how should it cool? So let's put on our sort of thinking hats here. Say, all right, we're thinking about temperature. And we're also in differential equations. So we should really start to phrase things in terms of change. So if I'm thinking about change in temperature, how do I think about that? T prime. So T prime says, how should my temperature change? Okay. So let's think about what should be true. Well, we probably need one more piece of information. I'll call it little a, which is the ambient temperature. In other words, the temperature of the space that it's been put into. So if our temperature is below the ambient temperature, we should warm up. If it's above the ambient temperature, we should cool down. How can we capture that in our differential equation?
I want to say log function.
Well, I mean, guesses are, there might be a log function involved in some version, but not in Newton's one. So right now, one thing that can help us, here's sort of a clue of what we should be looking for. If we already are at the ambient temperature, what should be true? The change should be 0. It's like, I like this temperature. I find this a very relaxing temperature. I'm not going to change. So whatever we have T prime equals, if T and A are the same, T prime should be 0. So what's something that might do that? Yeah.
Subtract the ambient temperature from the temperature of the object.
Okay. So we can look at the difference. We can look at T minus A. Now let's think about if this is doing what we want it to do. So suppose our temperature of our object is currently above the ambient temperature. So in other words, I'm hotter than the space I'm in. So this would be positive. What would T prime be right now? Positive, which would mean my temperature would be going up. So if I was hotter, I shouldn't have my temperature going up. What should I be doing? I should be going down. Now we can also flip it around, of course. If I'm colder, so that would say T is below A, this would be negative, and it would say I keep getting colder. So what do we do to fix it? Put a negative in there. And then Newton said, you know what, we'll do one more thing. We'll throw in a K. This is universal. I just need some correction term. So that's it. And that's it. That's the Newton's law of cooling. This is it. And we just derived it. Of course, does it capture what we want to? That's a great question. Now what we have is a formula. Well, what can we do? Well, we can solve this differential equation if we had the right tools. And we will next week. But for now, I have a black box. So here's our differential equation. And after it goes through the black box, there's the function. So according to our formulation, if the temperature change behaves in the following way, it's negative K times T minus A, then our temperature is going to behave like the ambient temperature plus T naught minus A. So the T naught is what's the temperature at time 0, e to the minus KT. Now, the way we got from the left to the right is through that black box, and next week we will open that up. There are many, many black boxes this semester, many of which we will open, some of which we will not. Does this make sense? Well, one thing we can ask ourselves, first off, is does it work? You can verify, just take the derivative and plug it in and see if it works. It's not hard to do. It's a simple exercise. I'll let you do it if you want. But I want to ask more, does it make sense? So what happens in the long run? In the long run, the only thing where the time shows up is right up here in the exponent. What happens in the long run if we let time head off to infinity? What does it do? What? This part goes to 0, so the whole thing goes to A. Yeah. So this says in the long run the temperature moves towards the ambient temperature. Is that reasonable?
Yeah.
Seems reasonable. All right. I'll buy it. Good. All right. Well, there we go. There's Newton's law of cooling. Population. Oh, this is good. All right. Well, let's start with a very simple model for population. So one very simple model, oftentimes used, for example, for modeling bacteria growth, says the way that the population will change, and so P here is population. Whoop, if I can spell population, I almost spelled population. Okay, population. Okay, there we go. The idea here is, in any given time, a certain portion, let's say we have a big group of bacteria, a certain portion of the bacteria will reproduce. So that the way that the population grows, the change in the population is proportional to how much population there currently is. So that's a very simple model. So it just says at a particular time, some fraction of the population chooses to reproduce, and so that's capturing the change of population. This should look very similar, for instance, to radioactive decay. Radioactive decay works in a similar way. It says, hey, if I have a whole bunch of material, at any given time, a certain portion of it will decay, and so that's how my change in the amount of radioactive material behaves. The only difference is because in radioactive material, I should hopefully go down, there's a negative sign. That's the only difference versus this model for population. All right, and that's it. That's a model for population. Okay, great. Well, what can we do? we can analyze it. Now, we'll keep using our black box. You might think, wow, this needs a really big black box, but actually, I can put a big one because these are very simple. So if our population behaves where the rate of change is a portion of the population, then that really says that our population behaves like some P naught, which captures the initial population, e to the kt. And again, next week, we'll open up this box and we'll be able to solve it. You might think, wow, this feels really familiar. It feels a lot like what we just did with Newton's law of cooling, because it's a lot like what we just did with Newton's law of cooling. They almost are the same. What? People are recycling? Yes. We've been doing it for centuries. All right. So, our formulation, this is how the population should change. We find what the function should do. Let's interpret it. Is this a reasonable model for population?
I don't think so, because our population curve's logarithmic.
Well, I mean, you can always put things in log-log scale. So we start with some initial population, and this says you behave like what kind of function? Exponential. So we start going up. And we keep going up. And up. And up. When do we stop? Never. So what's going to happen? We're going to end up with just ridiculous amounts of population. So this model says, you start with a couple bacteria, and then in a few months, you're going to have a set of bacteria the size of the solar system, because it's going to keep growing. Now, has that happened? No. No, the solar system is not just one big bacteria culture. At least I don't think it is. So there's problems with this model. Now, it's a simple model, and it's great to start there. But that says, hey, that's why we have to look at it and say, I don't know about this one. Let's go back and try something else. Okay, so what could we do? Well, our challenge is that we ran into sort of our problem was our population just sort of grew unbounded. There was nothing that said, hey, wait a second, you better slow it down a little bit, stop. Well, I have to be careful what words I choose here. Stop being so many. Okay, all right. Yeah. Definitely, I won't get in trouble if I say that. All right. So how can we do this? So instead of trying to, I'll show you one model. So this first one, we can think of this as being an exponential model, because we end up with an exponential function. So here's one approach. We have k, p, 1 minus p. Now I'm going to think of 1 here as being like, think of it almost like a percentage, like 100%. Now, that's maybe not so clear what I mean by that, but hopefully when we talk about that, it'll become more clear. This is called the logistic model. Now, before we look into the box and have it tell us what it is, let's see if we can't sort of get some feeling for what this should say. And one thing we can do is we can look at this differential equation and say, is there any really super simple solution to this differential equation? Does this differential equation have a really simple answer? Now, I'm not asking you for every answer. I'm just saying one particular answer, is it super simple? Okay, somebody said 1. Why is 1 an answer? What happens when you plug 1 into the right-hand side? You get 0. What's the derivative of 1? 0. So 1 is a solution. So here's a solution. Is there another simple answer? 0. And 0 is a wonderful answer for a population. It says, if you have no population, you will continue to have no population. That makes a lot of sense. The 1 we'll think about in just a second. We'll give it a name. Suppose I'm between 0 and 1. Just for a moment. And I should have said here k is positive. What's happening to our population? I'm not asking you what the function is. I'm just saying if p is currently between 0 and 1, say it's a half, what should be true about our population? It's growing because p prime is positive. I see p prime positive. That says I'm going to go up. So really in this region, my population is going uphill. Suppose my population is above 1. What's going to happen? What's happening to p prime? It's negative. It's going to go down. And it turns out that the curves do something like this. Initially, if you're close to 0, slow growth, the growth picks up, but around a half, it starts saying, whoa, we're sort of reaching some maximum capacity, and it slows down. So p equals 1, you can think of this as sometimes called carrying capacity, like what's the most we can take? And we can go up to that level, but we can't go past it because there's just not enough resources. On the other hand, if we start above 1, said, uh-oh, you're going to have to start shrinking, and it's going to go down. Is this a more realistic model? I'm not saying it's a perfect model, but is it more realistic? Yes. Now, someone might say, wait a second, Steve, what if population were negative? Don't ask that question. I mean, it's going to go down, but you might say, ha-ha, the model is flawed. Well, no, because you shouldn't have negative population to begin with. All right. You ready to see what the function is? The black box that will reveal it to us? There it is. So if p prime is k times p times 1 minus p, then p is, of course, haha, p0 over p0 plus 1 minus p0 e to the minus kt. And now that you see it, it's like, it's so obvious. Why couldn't we see it before? No. I will say that opening this particular black box is going to be fun because it's going to take us back to our Calc 2 days, our favorite part of Calc 2. Woohoo! Yes! And you're probably thinking, it was all my favorite part because Calc 2 is so much fun. That doesn't narrow it down any, Steve. So, all right. And I think this is a great place for us to stop.